So I've written it out a bit, save a bit of effort and a bit of time. It gets a bit intricate. So remember, we're trying to prove uniqueness. So that you can, for a particular element of your A, your abelian group A, it's of this form. Now these A's here are elements of your minimal, smallest, generating set, okay? And these powers here are of the form 0 or 1, okay? So to prove uniqueness, typically you assume there are two solutions and show they're the same. And I'm going to, well, Barnard uses an argument by contradiction. So assume there are two different forms. There are two different ways of writing this out. And here's one way, and here's another way. Can't write here, so I've spread it out over the whole board. Soon this will no longer be a problem. Okay? And we make the assumption that this eta 1 is the same as delta 1, eta 2 is the same as delta 2, and so on. And you just move from left to right until you come to your first eta, a position. So this would be the rth position, and that'd be the first position, second r minus 1th position, and the r plus 1th position, and the last position, the nth position, so on. So just move down from left to right. You're comparing the eta here with the corresponding delta here until you come to your first difference. Okay, and let's say it's at the rth position here. That's when you come across your first difference in the power. So now eta r will be different from delta r. Okay, so all this here and here the same. Okay, now to save me writing out all this garbage, right, I've just called that A, and it'll be an element of your group. Oh, it's a bit confusing because the group is also called A. But anyway, I've called that element A, and this part here after this, I call that B. I call this C, and not change, and the rest of it D. Okay. Now you have to get to this position before you got a difference here. So all this is just the same as all that. Okay. So A equals C by assumption, because there's no difference until we get here to the rth position. All right. So now the whole thing, all this is equal to all that, right? And this part, A and C, they're equal. So let's get rid of those. And now we've just left with this and B. So this is just this. So this and B, so that's this much from here to here. That will be equal to this and D, right? So if the stretch of my, I'll draw it from here to here. You can see that. Okay. So this and this will be equal, right? Because we cut that out. That is equal to that, but the whole thing, all three parts, is equal to all these three parts. Okay. We can cut that off, and that just leaves this part. So this times B, that times B, is equal to this times D. This is D here. Okay. All right. All right. Now this is just an element, right? You work all this out, and it just still comes to an element of your group. So this B is just an element. So it'll have an inverse. So post multiply on the right hand side by B inverse, both sides. This B will disappear, and you'll get B inverse here. Okay, so you know what that is. Now Now, post-multiply by the inverse of this. So, so you get, here's the inverse of that, and hold on. Sorry, this should be on this side. Okay, this, yeah, I've made a mistake here. So this should be on this side, right? Now, if you do that, this inverse and that cancel, and you're just left with db to the minus 1, right? So I'll make that well, it's still actually okay. So it'll be e to the r minus, well, minus delta plus e to the r, which is the same thing. All right. Okay. So so we know. So this is just this. But what is this? Look. This is the rth position. Okay, here, and that was, we assumed that's when, for the first time, the exponent here is different from this one. So epsilon r is different from delta r. Okay, so this power here, this exponent, it cannot be 1 and 1. It can't be 0 and 0, because both those cases are the same. So it must either be 0 and 1, or 1 and 0. Follow that logic? Okay. So that means that this exponent, this power here, is either just, so if it's 1 and 0, then you just have 1 here, or if it's 0 and 1, then you have minus 1. Okay, but this element is a member of the minimal generating set. It's just an element of your group. Okay, and all elements, if you square them, you get e. So that means that the inverse is equal to itself. Let me prove that. So any element squared gives you e. Okay, so a squared gives you e. Now multiply both sides by the inverse. So a inverse a squared is just a inverse. Okay, and this is the same as a to the 2 minus 1, which is just a, but that equals a inverse. So the inverse of a is still a. Right? The inverse of a is a. So this is just this. But that's that. So both of them are equal to a to the r. Right? So you can rewrite this as a to the r. You with me? We're trying to derive a contradiction here, right? Okay. So this boiled down to just this, a to the r. Okay. But this is equal to dB inverse. So this is equal to dB inverse. Now have a look at D and have a look at B. Here's your D. Look, it involves it evolves the elements a of r plus 1 to a of n. And it involves the b of inverse. Now the inverse of all of these is just the same. So the inverse of a r plus 1 is the same thing. Now we just prove that here. Similarly here. Okay. So what I'm trying to say is this this term here will depend on not n elements, it will depend on n minus 1. Now proving that's a little bit tedious, let's leave that as a homework question, but you can show this element here, the rth one, which equals dB inverse, this term here depends on only n minus 1 elements. Okay? So that means one of your members of your minimal generating set can be written in the form of the other n-1. So that means this one's not used in a sense. You don't need it because you can write it in terms of the other n-1 members of your generating set. So that means your generating set is no longer minimal because now it's gone down by 1. You've gone from n elements in your MGS, minimal generating set, you've gone from n down 1 to n-1. You've got a contradiction. So this AVR here depends on the other n-1 elements. So you can then use n-1 elements to generate all of the whole group, right? But that's a contradiction because we started with we said that n elements is the minimal generating set. Okay, so we've got a contradiction. So go back to your original assumption and falsify it. Now, what was our original assumption? Well, that there were two ways of writing this, and assuming that and that, we got this contradiction, and we then found a generating set that was one element smaller. Okay, so hence a contradiction. Therefore, the assumption that these two are different, that's false, and therefore they're the same. Okay, so quite an elaborate proof. And that means, now forget all the details now, just concentrate on the final result. It means that any element of your abelian group, where every element, when squared, gives you the unit, in other words, this, when that's the case, every element can be written in this form. As a product of powers, and these powers can be 0 or 1, that's it, of the elements of your minimal generating set. Okay, so you have that. Now, so what? It may not sound like much, but the theory that comes later relies on this heavily, and you can go a long way with it. So it's really worth getting this under your belt. It's a bit tedious, but important. And I'll stop there for a moment.